Thank you very much. As he already introduced, I have been working on streaming stuff. So basically, I have the similar disclaimer as Mark. I am not a database person. So if at this any point along this talk, if I'm saying something that is not the kosher thing to say in the database world, advance apologies. So I've been working on streaming stuff during grad school in AMP Lab, UC Berkeley. I was working with Professor Jon Stoica and Scott Schenker. Currently, I'm a software engineer at Databricks, which, if you're not familiar with Databricks, it is the company started by the people who founded Spark, including Matei Zaharia, who is a professor in Stanford right now. So I continue working on streaming stuff, and along the way, we have learned a whole bunch of lessons that has led us to go beyond streaming into building a data management solution, and that is what I'm going to talk about. And I'm going to, and my talk is going to focus on the lessons we have learned while using open source solutions and how it led to us building something hopefully better than what open source solutions currently provide. Anyways, so starting from the absolute basics, it's building a data analytics platform that can take real-time data from many different sources, and trying to extract insights out of it is hard. I mean, there are many different components, ML, given before ML, basic extracting and cleaning of the data, ETL and stuff is often hard. And traditionally for many years, and it still continues to happen, the way it is often done is you have a complex ETL process that cleans up the data, converts from unstructured to structured, and writes it up into data warehouses. And then from data warehouses, you have further levels of processing, etc., to do different kinds of processing, be it SQL, be it other things, to get insights out of it. Now, the problem that people faced with data warehouses has been, and this is like a very high-level statement, is that they're often these complex these ETL pipelines were often complex and really hard to manage, because you have to force the data into a structured form before it is this, and for a long time the frameworks that could do this were very ad hoc and unstructured, and so this caused delays in the entire end-to-end process. And often what used to happen is that these ETL used to be done in daily dumps of data into the databases. So from between the time when the data arrives and when you can start analyzing it for getting insights, there used to be 12 hours or 24 hours of delay. Then these workloads, because data warehouses were were so close to SQL, used to be limited to only SQL workloads, and doing anything further into advanced analytics like ML and stuff required a lot of hoops and etc. to port out the data, etc., etc., etc. It was complex, and of course, in any commercial solution, performance used to come at a very high cost, because things didn't used to scale very well, and therefore it required scaling up, which means paying a lot more money than scaling out and stuff. And that's where the whole data lake phenomenon happened, where your data could be stored in storage systems that could scale out. You had frameworks that could process data, MapReduce, etc., could process data in a scaled out manner, and data used to be stored in more open formats, not in proprietary formats inside databases, but open formats, so that not just big data processing frameworks, but also ML frameworks, etc., could access the same data and get insights out of it. And that's where earlier part of this decade Spark happened, and Spark was the first engine that could unify that in the same framework with the same APIs. Essentially, you can do both ETL, the ETL stuff, batch, streaming, work processing, etc., as well as SQL, ML, etc. So that's where Spark happened. Now, basically, that it meant that having a same API for doing batch and stream processing essentially simplified ETL. You could build your ETL logic, test it on batch dumps of data to kind of fine tune it, and take the same code and then run it on a streaming fashion for continuous ETL and stuff. And then basically that allowed that raw unstructured data from your streaming sources could be available as for analytics within minutes, if not seconds. And therefore, the workload also kind of exploded that you're not limited to just SQL and BI. You can plug in ML, everything, be it Spark ML or any other ML frameworks that you can think of can work with the same data. It is not locked in behind the database's proprietary formats. And therefore, overall, since it can scale out, you can use commodity hardware, it becomes cheaper, etc. But that was the earlier part of this decade. Now, as people started building big data solutions and data lakes, etc., people started realizing that the data lake doesn't solve everything. It has its own challenges in practice, and it took the industry quite a while to realize the actual problems in practice. And to kind of explain what those problems in practice are, let's walk through the problems we faced while we were building our own ETL pipeline. So for those who are not familiar, Databricks basically runs Spark in the cloud, both Azure and AWS. And so we have this service running in the background, we are collecting logs, etc. And we pipe it through Kafka, Kinesis, different solutions. And effectively what we want to do is we want to store them for streaming analytics, for real-time analytics to see what's going on right now, as well as for historical analysis. So we wanted to store it in some sort of data lake solution. And then we want to do daily, monthly reporting as well. Now, how do we do this? And we did almost till now 4 different versions, iterations of this end-to-end pipeline. And this is what I'm going to talk about, is essentially the third one, which worked the longest for very well until it didn't, because it just couldn't handle the scale at point, and that's where we started building Delta because of lesson learned. But these are what at a high level what happened. So for the streaming analytics part, we decided, okay, let's just continue processing in Kafka through Spark streaming earlier, then Spark structure streaming now. Well and good, but you can't store very long-term data in Kafka, so we ran for historical analysis, we stored the same data in a different pipeline started dumping it into open formats like Parquet, etc., into a data lake on S3 or Azure Blob Store and stuff. Well, this is the typical Lambda architecture that you may have heard of and stuff. We started with that process as well. And quickly we learned that there are problems to that. Oh, so from the data lake we could do reporting, etc., well and good. But as we started working and our application changes, service changes, etc., we realized that there's a lot of complication with the Lambda architecture, that random things can happen. For example, your log may get corrupted in flight before entering Kafka, or Kafka rotation drops and therefore something happens, your data may be corrupted internally because some field goes missing, some application writer pushed some incorrect code which stopped generating certain columns in your JSON data, and so all sorts of things started going wrong. And there was first of all, there was a drift between the real-time processing on Kafka, as well as and drift between that and the historical record. So we had to add these additional validation steps to make sure that they don't drift apart too much. We find issues that, oh, this column got dropped. Suddenly, oh, today's Parquet file stopped generating this column altogether. How do we reconcile yesterday's data with today's data, etc.? Those sort of stuff, which essentially means that we needed to go ahead and add reprocessing logic in the whole entire pipeline, which basically went ahead and cleared up these corruptions, etc., added columns when they were missing and things like that, and which also ended up partitioning the entire data into by date or some columns, so that when you're querying, you are reading only one subdirectory in the partition and not. So all the standard stuff. I mean, every data engineer trying to design a data pipeline in any company has faced all these sorts of issues. Just highlighting some of them in the context of what we faced. And so this reprocessing ended up basically causing additional complications that we had to deal with, because you cannot so your reprocessing essentially we had to decide whether to reprocessing would write into the same location as the streaming pipeline is writing, what are the consistency guarantees, etc., which basically there was none, because you're just dumping Parquet files. There's no control in that. If there was issues in the production, like if there was a failed job that started creating corrupted Parquet files, etc., how do we deal with that? All sorts of them. Anyways, details. The other major problem we realized that if we try to dump the data into the data lake faster, so that the data becomes available for analysis, it also means that we are dumping that data into smaller and smaller files. So which causes further problems that you have a lot of tiny files, and no processing system, be it Spark, be it any other framework, can deal with a lot of small files. It slows the entire processing down, which again slow down reporting, etc. Which means that we have to go ahead and add additional processes to daily compact the tiny files into larger files, etc. And we ran into these sort of issues that, oh, the compaction job is going on right now, which is rewriting the files in that table. Do not run your reporting now because it will see inconsistent view of the data. It will see the same data twice, etc. All of these are problems. Anyways, I went through a lot of details, but rather than getting lost in the details, let me actually characterize at a high level the essentially two sets of challenges that data lakes have. One is reliability. One, when you have any job failure, etc., that causes file corruption or impartial files, etc., it is very tedious to recover out of them. Two, there's a lack of consistency guarantees whenever multiple writers are writing into the same location. These are known problems. And then lack of schema validation, because you can dump Parquet files of different schema at the same location, different writers, and at the read time you have to validate the schema and deal with any inconsistencies between them, schema merging, blah, blah, blah. And the other category is performance. When you have a large number of small files or very, very large files, you don't, processing engines, even Spark doesn't really deal with it very well. They have other problems like even the storage layer, you're writing to S3 with a very, very large number of files, millions and hundreds of millions of files in the same S3 bucket. Even S3 doesn't deal with that very well, listing everything becomes slower and stuff. And then the partitioning structure that most people use in the data lakes are essentially a very, very poor man's version of indexing, which does not work well if you have a column that has very high cardinality or doesn't work with many dimensions. And so, and neither the storage system nor the processing engine can deal with these stuff very well. So, from a different point of view, what we would love to have is essentially the best of both worlds. One, you want to have the good of the data warehouses, which gives you pristine structured data, transaction reliability, and fast SQL queries. But you also want them to scale out. You want the data to be stored in open formats, and so that you can do mixed workloads on top of that open formats. And that is what was our motivation in building Databricks Delta, essentially which provides the scale of data lakes and the reliability and performance of data warehouses, and it works fast enough that it is low latency enough that you can use it for streaming. At its heart, it's essentially a scalable storage plus a transaction log. There are no really, from really database principles point of view, there are no really surprises here. So we're just taking a lot of pages from the database world and applying it in a distributed fashion on a data warehouse world. And that came with it a bunch of interesting implementation and system challenges to make it work with cloud storage, etc. I'm going to go through some of it. So for scalable storage, we essentially store the data in open formats inside a directory, Parquet table, similar to data lake fashion. And the transaction log is also stored within the directory in this special subdirectory called delta log, and that is and which is also stored in that same scalable storage, so that we don't have to deal with scaling the storage side part, because cloud providers have already solved that problem of how to scale the storage so that it can be accessed from hundreds of different Spark clusters and stuff. Now, this log is essentially like the sequence of ordered atomic commits, where each file essentially is a single commit containing a bunch of different actions. So for example, the first commit stored as, again, just JSON open format is, says that the two Parquet files, so 0, 1 and 2 were added. and then maybe the next commit can say that, oh, these two files were removed, and they were probably effectively collapsed together into a larger third file. So these are actions, and these are stored as an order sequence of files. Now, just as with any log, the readers read the log in atomic units of the file, so that any reader which may read up till 0 or up till 1 will either see the two individual files or the collapsed third file and nothing in between. So it gives the consistency guarantees that data lakes don't have. Now, to make this log work, you obviously need mutual exclusion between concurrent writers. So if writer 1 writes the first file, the writers write the second file, and if both writers simultaneously want to write the third file, only one of them should be able to write the third one. Now, the interesting challenge here is that how do we make this work in cloud storage? Now, the problem with cloud storage frameworks is that different clouds have different semantic guarantees. For example, the Azure Blob Store and Azure Data Lake does not give an atomic file visibility guarantee. That is, basically you can start writing to a file and it becomes partially visible at this before the file has been completely written and closed, which causes downstream complications that when readers are trying to read that transaction log, it does not know whether the file has been completely written out or not. But what Azure provides is an atomic put if absent. So we can use that directly to say that whether 002.json exists. If it doesn't exist, create it. And if the second writer which loses will lose because put if absent already exists, checks that whether it already exists or not. So that is the guarantee Azure provides. So that actually was simpler, because in S3 provides atomic visibility of an entire file. However, it doesn't provide a way to check an atomic way to check whether the file exists or not. So it doesn't provide put if absent, and what we had to go and do is basically build a service that converted this essentially multi-writer problem into a single writer problem, right? That service became responsible for essentially writing all the files and checking whether it has written out that same file before or not, etc. Anyways, so stepping out now that we have this log with an ability to atomically write out files into it, how do we do the larger concurrency control between operations? So there's two ways of doing this: pessimistic and optimistic. So in pessimistic, the way we would consider doing it is basically all writers essentially hold this lock, which prevents other writers, and you start writing out all the data for your operation. Let's say you're doing an insert while holding this lock. The good thing is that it avoids any wasted work. You're not doing any work until you get the lock. However, the bad thing is that practically it was complicated to build a good distributed lock solution. And rather, what we realized that optimistic concurrency is enough, because the number of concurrent writers in typical customer workloads that we saw is relatively low. So which means that what we could do is that assume that there will not be any conflict, start writing out the data files. Once all the data has been written out, then capture all the actions of which files were added, which files were removed, and then commit that to the log, and then check, while you're committing, then check whether there was any conflicts with any concurrent operations or not. So yes, there is a slight chance that the work may get wasted, but overall the probability of that is relatively low, because the general concurrency is relatively low. And we found that it works pretty well in practice. Now for that, we basically developed this simple logic of how we detect their conflicts. This is essentially same as recording the read sets and write sets. So you record which version each operation or each user started reading on. You track what changes been made, and when you try to commit, you check whether there was any concurrent changes since the read version or not. So for example, if user 1 reads file A and tries to write B, whereas user 2 reads A and tries to write C, one of them would fail to write, but then the user 2, which if it failed to write, would check that, oh, the other changes since the version 0 does not conflict with mine. B and C doesn't conflict with each other, so it will retry and commit as the next version. So this will work. However, let's say in a different scenario, instead of the user A writes B but deletes A, and user 2 deletes A and writes C, then again they would fail. But here user 2 would see that the commit made by user 1 conflicts with it because it has already deleted A. So it doesn't, so A, since it currently doesn't exist, the operation A, delete A, add C is incorrect. So it will just fail the operation. And that is the risk we carry for doing optimistic concurrency, that some of your operations may fail. But in practice, we realize that if we give users guidelines on what combination of operations can fail or not fail with tunable isolation guarantees, tunable isolation levels, I think this works pretty well in practice. So going back to the challenges, how each of these are solved, reliability, failed production jobs leaving partial files doesn't happen because whatever files have been written out, be it partial or full, etc., is not visible to the readers until it is committed to the log. So that avoids that problem. Those files can be vacuumed and cleaned out of band. Then the lack of consistency is solved because all reads have full snapshot consistency, all writes are consistent. In practice, most writes don't conflict, and with guidelines, it works pretty well for many of the common workloads that we have seen in our customer base. And because of this log not only stores these actions of which at the file level guarantee, it also can store the schema and everything. So at the time of write, it can validate whether the schema is valid or not. It can validate whether invariants and constraints specified in this table are satisfied by that commit or not and stuff. So, and finally, in terms of performance, this becomes much easier because we have added this SQL operation called optimize, which essentially transactionally compacts small files into larger files, which can run concurrently and without affecting any consistency guarantee or any other concurrent operations and stuff. Now, the cool thing is that it was shocking how well this worked in practice, because we had this customer which had this giant table but with almost billions of files, and it was so bad that they had 32 large Spark clusters to divide that table into 32 partitions to process them, because they could not handle a single cluster, or a few clusters couldn't handle that level of small files. When we built this optimize for them and they tried that out, all that went away, and the workload that they had to that was forced to run on 32 different clusters could just run in one cluster. And it was shocking how sometimes these little bit of things can work well in practical workloads. The other cool thing is that to solve the partitioning problem, to do something better than partitioning, we added essentially multi-dimensional clustering, z-order, which again in the same command optimize, z-order. And to go a little bit deeper into the actual use case that actually motivated us to build multi-dimensional clustering is that Apple, more than a year and a half ago, came to us and said, we have this massive data set of more than 100 terabytes, and which is basically connection data. So they have data of connection between a source IP and a destination IP by date. I'm removing other columns for this discussion. And what they want to do is ad hoc queries either on the source IP or on the destination IP. Now, the problem with this is that for date, partitioning is fine because date is a low cardinality thing. Source IP and destination IP is a high cardinality, and partitioning just doesn't work. The file system can't handle it, the Spark can't handle it, nothing can handle it very well. So instead, what they were trying to do instead is essentially multidimensional sorting, which is a very common practice in the data lake world, where basically, just to illustrate, using this simple diagram that, let's say the source and destination IP are two-dimensional, these are the data sets. You sort them by source IP first and destination IP within that, and then we want to create files of the ideal size, and let's say in this case the ideal size of each file is four rows, four records in this. So with the sorting it will create 4 files. Now this works well for source IP because if you can directly skip all the data and just read 2 files. It doesn't work very well with the second sorting column because you really can't do much skipping. In fact, you read 8 files and throw away a bunch of the data because that's not useful. So, and Apple was not happy with this because when they're in a time crunch where they have some attack going on and they want to really quickly do analytics based on source IP or the destination IP or both, they don't want to be blocked by that, oh, if I query by destination IP, it's going to take longer, let me work around that and stuff. So they wanted something that works well in both dimensions, which is why we took another page out of the database literature and implemented multi-dimensional clustering. In this particular, we had used the z-order space filling curve, which kind of fills it up in this funny way. And we could use the same file size of 4 rows, but now if both the queries can read only 4 files, which is not the best case scenario, but it's reasonably better than reading 8 files. And so it is reasonably good for all the dimensions, and that made Apple much happier. Now zooming out at the higher level, what they wanted to do is they wanted to build this data pipeline, specifically the Apple's InfoSec team wanted to do this, and they wanted to basically build this pipeline that collects all their data center logs from all their machines, connection data, as well as other kinds of data, dump it in a place and do both real-time analysis as well as post-processing analysis. And when things go wrong, that they are detecting some sort of attack or something went wrong, they want to quickly go in and do ad hoc analysis to identify the threat and debug it and mitigate it. Now they were getting at the scale of more than 100 terabytes per day, so 300 billion units per day. So most solutions don't work at that scale. And what they had earlier is basically a combination of data lakes and data warehouses where they were dumping data blindly into a data lake and then doing this complex ETL to push it into different data warehouse solutions with different filters of the data. Such that because each data warehouse solution was good at doing certain things and not the other thing, etc. So they had this complex pipeline, which essentially took them 20 engineers, 24 weeks to build, and which it still caused them hours of delay because going through all these layers of data lake and ETL, data warehouse, etc. was tedious and time consuming. And it was not scaling because it was just getting cost prohibitive on the data warehouse side, whatever solution, proprietary solution they were using. And they could only keep 2 weeks of data in it, and so any historical comparison with, oh, this machine is having too many connections compared to this previous, what happened 1 week ago, they couldn't, or a month ago, is this anomalous, or they could not do those comparative analysis. And of course, they didn't have any hope for doing ML using those proprietary warehouses that they chose. Instead, once we gave them Delta, actually we kind of developed it keeping their use case in mind because of the scale having that scale is a good motivating factor. And so once we gave them, just 2 engineers took 2 weeks to port their platform to run on Spark, structure streaming, and Delta. And that further enabled them to add additional workloads like advanced analytics, stateful stream processing, etc., which they didn't have any of that earlier. So data was usable within minutes, some of them within seconds. It was much easier and cheaper to scale out, and they could store 2 years worth of data. So one of their largest tables right now has, well, right now, no, it's probably all of these are 1 year old stats. So 1 year ago, their largest table had 504 terabytes of data, 11 trillion rows, and they were happy with the analytics they could do on that. And to go back to our pipeline, just to kind of complete the loop of what we eventually in our fourth iteration, what built on Delta, what we could do is basically simplify the process much better. Instead of having this Lambda architecture between streaming side and batch side, we could just put everything through Delta, because Delta was fast enough for doing any kind, both the real-time analytics as well as storing historical data in large amounts. So the Lambda architecture went away. The validation process was not needed. All the reprocessing, compaction, etc., that needed to be done to clean up the data was much easier to reason about because of the consistency guarantees. You didn't have to stagger your reporting with the compaction so that they don't collide with each other, they don't happen at the same time. All of that went away. And of course, with the Z order, our ad hoc analysis also became much, much faster. Now, from the developer point of view, it is very easy to use Delta through the Spark APIs. Any Spark API where you specify Parquet as the format, you can just replace Parquet with Delta and everything just works. Everything gets taken care of under the hood and stuff. So now the other cool thing that I kind of missed in this entire discussion is that the key reason why we could handle this much scale is that we converted the metadata problem of storing millions and billions of files in the transaction log into a data problem, because with very large number of transaction log files, we could just use Spark to do the distributed metadata processing, and with scalable storage in the cloud, all of that problem, all that metadata problem just went away and became a data problem itself. Because before that, we had tried a whole bunch of things like, let's keep this transaction log into in a SQL server or a MySQL server. We just realized that that doesn't scale, because it's pulling out the transaction log, having 10 million files out of the MySQL itself took quite a bit of time, which did not scale out. And what happens when 100 different Spark clusters are trying to query the same transaction log, etc. That just didn't work. With this combination of solution of storing the transaction log as files in this cloud storage layer itself, solved that problem of scaling the metadata layer. Anyway, so I'm finishing up. This Delta is available as part of our Databricks Unified Analytics platform, which is a platform built using Spark, but not just Spark, on the cloud. This is my sales hat, putting on the sales hat. We are hiring, by the way. And if you want to really learn more about what's going on in the Spark and the data and the Delta side of things, Spark Summit is exactly 20 days from now, and please consider visiting the Spark Summit. You'll learn a lot more. And to finally summarize, Databricks Delta plus Spark together can handle the massive scale that data lakes are known to handle, but also provides reliability that data warehouses are known to provide, can do all sorts of indexing, Z-order, as well as caching because Spark is good at caching. All of that advantage are there that can speed up queries a lot. And more importantly, this is very important from industry point of view, stored in open formats like Parquet, ORC, etc., and can provide low enough latency for doing stream processing right out of it. Thank you very much.
Thank you very much, TD. You know, TD, I have to disagree with you.
Oh.
You introduced yourself and you said you're not a database guy. I'm sorry, but you're a database guy. You just talked all core database principles that the database universe has been thinking about.
I'm sure I bored some of the folks out here.
But you're a database guy. Okay. Sorry to disappoint
I will
you,
take
but
that as
you're
a
a
compliment.
database guy. All right, questions.
Yes.
Mike, there's a mic right in front of you. There you go.
Okay. Yeah. Sorry. Could you back up to the slide where you sort of started, going through the Delta is unified, like sort of you don't need the other things anymore? Because I just had a question about that.
Oh, wait, which one?
Actually, yeah. No.
This slide?
Go back one more.
Oh.
I had a picture with your flow. That's the one.
Oh, okay.
So kind of my understanding, because I don't sort of work in the data lake space, is kind of traditionally people would have gotten their favorite streaming engine, which you would hope would be Spark Streaming, or it might be Flink or something like that, and they would be processing their data on the incoming, right, to compute the kinds of analytics that you were talking about, right, over the incoming data. And then they would also be, sort of doing maybe things, using, sort of the more batchy Spark or batchy Flink or Hadoop on the other. So is one of the implications of this that, you really don't, like that first line, you don't need, let's say, a separate Spark streaming anymore, you just use Delta?
So, okay, so in our case, the latency requirements for our streaming analytics was enough that going through files with minute scale latency was fine enough that we could merge both these patterns together. I wouldn't generalize it to the general problem that, can we all do everything through Delta? No, and the moment you touch files on a cloud storage, you cannot do even second scale latencies. So yes, in some case, it all depends on what are your requirements. If you want to do, let's say, alerting at the second scale latencies, if not lower, then again, Delta wouldn't be the right solution. Keep it within Kafka, but you need to have another pipeline that will dump the data into whatever data lake or data warehouse solution you have. So yes, it's not a universal solution. It's all boils down to your
sort of moves the line, but
yes, there's a line.
Safe. Hi, TD.
Hi. It's been a while.
Yeah. So do I understand that Databricks Delta is just curated files in what's the format that you use?
Parquet.
In Parquet.
Yes.
Like curated and made it in a good size, and so that it will be easy for the next stages to do the work that you want.
Yes,
it's
basically that.
That's okay. Okay,
yes.
now
We're taking a lot of pages from the database world and just applying it on this, doing it carefully in a distributed fashion.
So that in the rest of the process, you are always working with these Parquet files and to make everything uniform and so on. Okay, thank you.
Jacek?
Yes.
So do you feel that the z-order curve is sufficient enough for partitioning? Because it solves a certain class of problems, right? But beyond that, would you be doing data duplication, or what would you how would you handle the more generic kind of, how would you solve the partitioning?
Yes, z-order does not solve the entire thing. So again, going back to that use case of Apple, their scale was so large that z-order was like the first step. We had to also build further things like Bloom filters, etc. All of that is being implemented. Again, more pages to kind of speed things up to the level where they are happy with the performance, as gave the same latency as their proprietary systems had. So yes, z-order is not the only solution. There is the need for more things like Bloom filters and stuff. But what we have found that only 0.01% of the customers have the scale as Apple has. For for 99.999 percentile of the companies, workloads out there, z-order is probably quite sufficient for many cases. And but you do need more things beyond that to scale it even higher.
Right. And do you expect the users will be doing that layer, or you will be implementing kind of in the future other types of indices and partitioning? Or?
So I don't think so our hope is that we will implement all of the functionality within Delta with just APIs for users to invoke. So it'll be up to the users we give the users the tool to decide whatever indexing or partitioning or z-order they want, whatever way they want to optimize. We just provide them the API tools for doing that. But whatever we need, we will implement it ourselves.
Other questions? Yes, sir.
Do you provide once and only once semantics here, or what's the consistency story for?
Yes.
Okay.
The short answer is just yes. Yes, this whole pipeline we give the exactly once guarantees and stuff. Because Spark, structured streaming, and has always been exactly once with respect to files. With Delta, it is no different. It is actually even better. It is even better. Structure streaming plus Delta is even better than structure streaming plus files, because earlier in Spark, you could not have multiple streaming pipelines writing to the same locations. But with the Delta, you can, because of the additional metadata, et cetera, and stuff.
One more question. Katie?
Just something I was thinking about, your transaction log, in which you have sort of these atomic commits, sounds kind of like Git. Do you see any parallels between them, and could one learn from the other?
It is actually much simpler than Git. It's not a hash chain. It's just files. So, but there is, and we do use checksums and stuff to make that more perfect, but we don't make it a hash chain. Actually, maybe we effectively do. I think that, though, yes, to answer your question, there are definitely lessons that can be learned from it. It's just about requirements. Whatever we have implemented right now, it's sufficient for whatever workloads that we have seen till now. If there is anything or any sort of corruption or comparison, etc., that are not yet solved, yes, there are lessons we can borrow from Gits and stuff like that.
All right, thank you very much, TD. That was a great presentation, and congratulations on becoming a database guy.
Thank you very much. You have a wonderful audience.
All right, we are on schedule, so we're going to take our coffee break now. Please be back at 10:50 for the beginning of the next section. Thanks a lot.